This episode is sponsored by Squarespace.
Getting a rocket safely into orbit is not easy. Sometimes just getting it off the launch pad can prove difficult. The challenge is even greater when it's your very first attempt with a brand new vehicle.
First motion.
Elon Musk recently stated in an interview that he gives Starship a 50% chance of successfully reaching orbit during its upcoming flight test. Now, Elon does have a tendency to undersell things at times, especially when you consider the fact that he also gave Falcon Heavy a 50% chance of success on its maiden flight, and look how that turned out. Falcon Heavy was the first launch I ever experienced in person. And as we sat on the beach for hours hoping that it wouldn't get scrubbed, I couldn't help but to wonder about that other 50%. Is this just some arbitrary number that Elon threw out there, or do they already know where they expect it to fail? 5 years later, we're now just weeks away from the first ever Starship orbital test flight. But this time around, we believe we know exactly what SpaceX is worried about here. A complete structural failure of the Starship second stage roughly 1 minute into flight.
This will be a very critical moment for Starship. And after today, you'll have a much better understanding of why that is. My name is Zach Golden, and welcome to another CSI Starbase Deep Dive Investigation. Hey everyone, thanks for joining us. Before we get started, I should probably point out that this is actually part 2 of a multi-part series investigating the complete historical timeline of structural verification testing for the Starship program. In part 1, we discussed each of the 24 test articles and Starship prototype vehicles from 2019 through the first half of 2022. We learned about every success and every failure that occurred during this time. We placed a lot of focus on failures because a lot of the most important changes to the new iterations in the design of Starship are a direct result of these events. If you haven't watched that yet, don't worry, because although this deep dive investigation is intended to build upon what we learned in part 1, you should be able to follow without having seen it. Today, we'll be focusing almost entirely on Ship 24 and Booster 7, so we can truly get to know these vehicles inside and out. But first, I realized at the end of part 1 that there were some important things about Ship 20 and Booster 4 that shouldn't have been left unsaid. For a lot of folks, it was incredibly disappointing at the time that these two vehicles didn't end up being the first pair to perform an orbital flight test. But there is something that we should always remember about Ship 20 and Booster 4. These two vehicles were the pathfinders for a very long list of events.
Ship 20 was the first ship with a full thermal protection system, the first to have 6 engines mounted onto it, and also the first to fire 6 engines at the same time. Which was also the first time the vacuum version of the Raptor engine was ever tested on a vehicle. Booster 4 was the first and only booster to have 29 engines, the first to receive grid fins, aero covers, and engine shielding, and also the first to have a Starship stacked on top of it. Both of these vehicles performed an extensive list of tests that helped SpaceX verify design changes to the Starship. But they were also used as test subjects for another purpose as well. When it comes to certifying the ground support equipment, there's only so much you can do without having an actual vehicle to test it on. So for this reason, whether it was going to fly or not, SpaceX needed Booster 4 in order to test fit the hold-down clamps on the launch mount for the first time. They also used it to test fit the booster quick disconnect and later the 20 Raptor QDs, which are used to start up the outer 20 Raptor engines. They used it to test the gas distribution system for the orbital tank farm, including the liquid oxygen and methane pre-pressurization system, and loading of the composite overwrapped pressure vessels. They tested propellant loading and the detanking process for the first time using Booster 4 as well. That one in particular could be a pretty dirty process, considering that the booster is basically being used as a massive basket strainer for cleaning out all of the residual foreign objects and debris left over in the cryopipe system after construction is completed. Booster 4 was also used to test the igniter system, which delivers high-pressure oxygen and methane to the igniters for the outer 20 Raptor engines. Moving back to Ship 20, It was the first vehicle to be lifted by the chopsticks, allowing SpaceX to verify the functionality of that design and dial in its performance during stacking operations. Ship 20 was the pathfinder for testing out the Starship GSE arm and quick disconnect umbilical. And finally, it was used to test out the propellant loading system of the Orbital Launch Integration Tower, just like the booster did for the launch mount.
There are tons of others that I have left out, but I think you get the point. Ship 20 and Booster 4 were straight up workhorses, even though they never reached the final milestone. So now that we have the obituary for Ship 20 and Booster 4 out of the way, let's move on and discuss the current generation of Starship, because there is a lot that we have to cover. Once again, we will need the assistance of Special Agent Jax from the Ring Watchers, who we uploaded into the CSI Starbase artificial intelligence system a few weeks ago. Glad to have you with us, Jax. Yo, why are you so tiny?
Well, some of the folks in the comments from part 1 said they didn't like my little avatar.
Yeah, I saw that. I mean, it is kind of creepy. But don't worry, I got a firmware update for you. Although since you're a bot, you probably could have done that yourself, right? Anyways, I also noticed in the comments that a lot of folks feel like the Ring Watchers need to create their own website to store all of the information that we're covering. It would probably end up being one of the most detailed wikis available for Starship.
Sounds pretty time consuming.
Well, it doesn't have to be. Thanks to Squarespace, who's the sponsor of today's investigation.
What is Squarespace?
Check this out. Squarespace is a website for building websites. It's like website inception. Within minutes, you can get started building out your site using their wide variety of styles and their award-winning template library that can help give your website its own unique personal touch. You can even create a digital archive of photos and videos thanks to their unlimited storage space, which makes it really ideal for photographers or anyone who needs to create an online portfolio to showcase their work. Squarespace even allows for easy management of premium content, donations, and merchandise. I mean, look at this. You can design your own merch within the built-in editor or import your existing designs from external sources. Look how quickly I created these CSI Starbase hats.
I'm assuming this means you'll be making these available soon, right?
I mean, at this point, I really have no excuse anymore. I didn't realize how easy it is to create these hats when I started, and now I'm pretty upset that I didn't do this earlier. Anyways, if you want to try it out for yourself, head over to squarespace.com/CSI Starbase and get 10% off your first website or domain. You can find the link to that in the description. So before we can explain why SpaceX is worried about a catastrophic failure of the vehicle during Max Q, we need to understand how we got here in the first place. So let's get to know Ship 24 and Booster 7 a little better by reviewing all of the important events that have occurred since flight readiness testing began in March of last year. It's been an incredibly long journey to get them ready for this first orbital flight test, and there have been many complications along the way that could have forced SpaceX to scrap both of these vehicles. As we go through this, keep in mind that Starship is still relatively early in the development phase. SpaceX's iterative design approach involves constantly testing and improving their rockets through multiple design iterations. While this approach has many benefits, such as allowing for rapid development and reducing costs, it can result in problems if not managed properly. One potential problem with this approach is that it may lead to a lack of thorough testing. This problem gets amplified if design and manufacturing teams start to outpace the testing process, which I think is exactly what's happening here. I don't think this is due to a lack of foresight or competent management, however, because SpaceX has a ridiculously talented team of engineers leading this project. In this case, the early retirement of Ship 20 and Booster 4 forced them to move up the timeline on the next generation of Starship much earlier than planned, and everything we are going to discuss today is a result of that unfortunate situation. All right, take it away, Jax.
We'll start off with the one and only Booster 7. Love it or hate it, you can't deny that Booster 7 has been through some weird stuff. It was fully stacked on March 10th of 2022 and rolled out to the pad at the end of that month. It conducted a pretty uneventful cryogenic proof test on the orbital launch mount, which was the first time a super heavy booster had ever been fully filled with cryofluids. This is when SpaceX decided that it was time for Booster 7 to go through some thrust ram tests. Because B7 was in this new generation of vehicles, it was the first to use the new Raptor 2 engines, and the first to sport 33 of them rather than 29. This meant a new thrust puck and a wider hole in the dome for it. If we pull up Booster 5's 9-engine thrust puck, we compare it to Booster 7's right here. If you aren't sure what a thrust puck is, we discussed that a bit deeper in part 1 of this investigation, but essentially it's the plate that takes the forces of the inner cluster of gimbaling engines on both the booster and the ship. But back to these booster pucks, not only do they have very different methods of machining, but they also vary in size. The 9-engine puck is about 4.8 meters across, whereas the new 13-engine puck is about 5.6 meters across. This also meant that the can crusher test stand had to be tested in a completely new configuration from how we saw it used in part 1 of this deep dive investigation. As you can see, on the concrete pad in the center of the structure, 13 thrust rams were arranged to test the center gimbling engines. Without placing the cap on top of the booster and using 140 meters of rope to pull down on the top, there was no way that SpaceX was going to be able to perform max Q testing on the vehicle. So it looks like this test was primarily for testing the thrust-bearing structure of the booster. So, SpaceX lifted Booster 7 off from the launch mount and carried it over to the can crusher, and attached the 13 hydraulic pistons to the booster's center engine mounts. They eventually conducted a test using these thrust rams on April 14th of 2022. And it looks like B7 passed with flying colors. SpaceX started detanking Booster 7 with the intention of sending it back to the high bay for installation of its 33 Raptor engines. Unfortunately, the next day we found out that this test did not go as smoothly as we initially believed after SpaceX crews opened the hatch to the liquid oxygen tank of the booster and began inspecting the interior with a long fiber optic camera. I'm sure that many of you watching this video know by now what I'm referring to. But what exactly happened during this test, Zach?
Oddly enough, this is actually something I covered in my first ever YouTube episode on April 29th of 2022. This was the test when Booster 7's downcomer failed during the detanking procedure. As Jax mentioned, everything was going well during the first part of the test, but as they say, it's not over until it's over. So, after the thrust ram test was complete, SpaceX began to drain the fluids from the liquid methane and oxygen tanks.
When the detank was almost complete, they started to depressurize both tanks, which is a common thing to see near the end of the process. The methane tank was vented in short bursts to release the pressure, but the liquid oxygen tank was vented continuously for nearly 20 minutes nonstop. When it reached the point where it seemed like there was barely anything left in the LOX tank, SpaceX opened a single vent on the methane tank for a final time, which only lasted for about 10 seconds. 5 seconds after it stopped, Lab Padre's Rover 2 camera picked up the sound of the internal collapse of the downcomer inside of the header tank, and the effect of that violent action was visible on the outside of the booster, as you could see a line of frost falling off of the LOX section. Using this animation from 3D forensics agent Chameleon circuit, we can see what this downcomer looks like as it's passing through the LOX header tank. Keep in mind, this part is speculation, but what we believe happened here is that during the final depress vent of the methane tank, the downcomer was completely empty or close to it. The LOX header tank was more than likely still filled with fluid, or it was at a significantly higher pressure than the void space on the inside of the downcomer. When the vent on the methane tank opened up and dropped the pressure even further, the pressure differential between the header tank and downcomer became too great and caused the downcomer to collapse in on itself like this.
It's a really good thing that this test was using liquid nitrogen in the methane tank, because had this happened under different circumstances, it could have resulted in a rather large explosion, even though the tanks were near empty. This procedural failure ended up functioning as an unintentional structural verification test for the methane downcomer tube. SpaceX was able to remove it and install another one piece by piece. But this time, we believe they welded extra hoop stiffeners around the transfer tube.
We have seen the methane transfer tube on future boosters receive significant reinforcement upgrades. Not only did they increase the number of ribs on the tube, but they also stopped using a singular strip of steel that could easily crinkle up like a bag of ruffles. In the newer design, they now have thicker ribbing, and it appears to consist of 2 discs welded together, which is only noticeable because of the weld marks that join them together. On top of this, there is a flat strip that forms a 2-sided trough, which might also function as a slosh baffle to some degree.
Returning to Booster 7, the downcomer replacement took just under a month to complete, and on May 11th of 2022, it performed another cryo test to verify that the repairs were acceptable.
So once Booster 7 had completed this re-verification cryo test, and proved that the newly replaced downcomer section was structurally verified, it rolled back to the Mega Bay once again to be prepared for static fires. During this downtime, SpaceX rolled out their brand new Starship prototype that they had produced. Like Booster 7, Ship 24 sports numerous design changes compared to its predecessors, many of which changed the structure of the vehicle. First off, SpaceX heavily redesigned the aft section of the Starship. With the switch to Raptor 2, the dome was modified with the brand new mounts for these engines. However, it's important to note that the general design of the thrust puck itself is still similar to SN15's, which we discussed in part 1. There are a load of other changes, but we'll discuss those a bit more when they become relevant. So on May 26, 2022, SpaceX rolled it out to the orbital launch site Cryo Station by the tank farm. If you aren't aware, the Cryo Station is a location where the ship can conduct proof tests right on its transport stand. The reason the ship was tested here was because SpaceX was still in the process of upgrading Test Stand A to support the new changes to the quick disconnect panel on this generation of Starship. When it arrived, SpaceX set up for the first pneumatic proof test, or ambient proof test, using gaseous nitrogen to bring it up to pressure. How did that go, Zach?
Well, this is another topic I've covered in a past episode, so I'll make this a quick review. Unlike the Downcomer collapse on Booster 7, where we didn't find out about the problem until the following day, it didn't take much to recognize that there was an issue the moment this occurred. You could very clearly hear the sound of the pop, which was followed by about 20 thermal protection tiles falling off of the ship. In contrast with a lot of the events that we covered in part 1 of this investigation, Allan hasn't been as forthcoming with details about incidents like this, so we're forced to do the detective work ourselves. Thankfully, SpaceX decided to repair the damage at the launch site, which is the only reason we know what occurred during this test. So let's take a look at the inside of the nose cone so we can see what's going on here.
At the top of the nose cone, there are 2 header tanks, one for liquid oxygen and the other for liquid methane. Each of these tanks require a pipe for filling and draining liquids and also for tank pressurization. The ones for pressurizing the tank are the 2 smaller lines on the left. In Ship 24, these were originally designed to be straight pipe sections going all the way from the top of the forward dome to the header tank above.
Unfortunately, this design didn't account for the effects of large temperature swings inside of the stainless steel piping. So as SpaceX went to pressurize the header tanks, there was likely a large temperature increase causing significant thermal expansion in the pipes. This thermal expansion caused the pipe to buckle, which is what created the loud pop that was heard during the testing event.
A few days later, Starship Gazer live streamed as SpaceX engineers removed the damaged section of pipe, allowing us to see the bent section as it was extracted from the payload bay. It was replaced with a new section of pipe containing U-shaped expansion loops, which would allow it to have more freedom to expand and contract.
This was a great thing to figure out on the ground instead of during flight, especially since any issue involving the header tank is going to occur when the vehicle is coming in to perform its landing maneuver.
So once this repair was completed, SpaceX was finally able to perform its first cryo test of Ship 24 on June 2nd of 2022. With the first cryo-proof test successfully out of the way, and upgrades to Pad A's new quick disconnect now completed, Ship 24 moved to suborbital Pad A. Once there, it conducted 2 additional cryogenic proofings using the 6 thrust rams underneath of the vehicle, like Ship 20 used in 2021. On Ship 24's aft dome, the stiffening structures around the Raptor vacuum mounts had been redesigned, which is why we saw the thrust rams get used again. On Ship 20's generation, these were mounted on the exterior face of the dome. Ship 24 Plus has them on the interior. The first test on Pad A was on June 6th, followed by another the next day. From here, with the cryo-proofings out of the way, Ship 24 was dismounted from suborbital Pad A and returned to the production site to receive its 6 Raptor engines and other finishing touches. But now, it was time to start doing some quick testing, because Ship 24 and Booster 7 were both already receiving engines, and there still hadn't been any test tanks to verify the upgraded designs. So SpaceX constructed Booster 7.1 to verify the design of Booster 7's aft section. B7.1 is a test article made out of a 33-engine aft section designed to be used on the can crusher in the 13-engine configuration. It's sort of the same concept as B2.1's test in 2021, where it was testing the integrity of Booster 4's generation aft section, as we talked about at the end of Part 1. This test tank featured long stringers on the bottom of the aft section, which was also something that they added to every booster that came after the failure of B2.1. So part of the goal was to not have the aft section fail in the same way that it did in the previous test. The last thing to mention about B7.1 is that it had stringers added on the forward dome in order to allow the can crusher cap to be mounted on top of it. But this wasn't an actual booster forward dome being tested this time. It was just a leftover Starship forward dome they had lying around. This is how we know they were only focused on the thrust-bearing structures of the booster with this test article.
Hold on, Jax. I'm going to cut in here for a second because I think it's probably a good idea that we briefly explain what a thrust-bearing structure means in this situation. So let's start off with the center 13 engines. The largest of the thrust-bearing structures on the booster in terms of overall surface area is the aft dome. While the center 13 engines are firing, there will be a force pressing upwards on the thrust puck.
that force must be transferred from the thrust puck to the aft dome and then to the outer walls of the liquid oxygen tank. This happens along the point where the aft dome is welded. This is part of the reason why it's important to have these extra stringers around the weld line. So next we can consider the outer 20 Raptor boost engines. This is pretty straightforward, literally, because the thrust is directly transferred through the aft skirt to the walls of the LOX tank section. That's why the additional stringers on the last ring section are extremely important as well.
Anyways, B7.1 first rolled out to the pad on June 16, 2022 and was set up on the can crusher stand 3 days later. One interesting thing to note is that with B7.1, the thrust puck did have 13 engine mounts, but it was not the same design as Booster 7's. SpaceX had already verified B7s during its own cryo-proof testing. So, they decided to put Booster 9's revised thrust puck on 7.1, which meant that in the future, Booster 9 would not have to go on the can crusher. This was pretty cool, as it would ideally speed up the future testing campaign. There were some important changes with how the can crusher was configured for this test that I will allow Zach to explain here.
Allow? Anyways, this is honestly one of the most peculiar configurations that we have seen the can crusher arranged in thus far.
What was unique about this test that we hadn't seen previously is that SpaceX also decided to add additional pistons to test the mounting points for 3 of the outer 20 engines. This was difficult to notice. If not for the missing catwalk platforms in the center, we probably wouldn't have caught it. But you can see that tucked way back there in between the hold-down clamps are 2 pistons. After we noticed this, we were able to go back and look through the footage from NASA spaceflight when the can crusher was rolled out. You can see them sandwiched between the columns for the 20 booster clamps. Looking at it again a few days later after it arrived at the launch complex, we can see that there was an additional thrust ram added before Booster 7.1 was placed on top.
The reason I find this interesting is because it means that SpaceX decided to use the results from a localized test of just 3 engine positions, instead of performing this test on all 20 to verify the structural integrity for the entire thrust-bearing structure of the vehicle. Now, this isn't to say there's anything wrong with that, it's just an interesting observation.
B7.1 started off its 4 cryogenic tests on the can crusher on June 28th. This test was one of the more interesting ones to watch, because we were able to clearly see the pistons on the can crusher being pulled down repeatedly. Each time the pistons pull down is considered a cycle test. This is similar to the testing that Zach mentioned was performed on Falcon 9 back in Part 1. Falcon 9 performed more than 150 cycle tests, but unfortunately we weren't able to determine how many were conducted on the B7.1 test tank. This structural test was followed by 3 additional ones on July 19th, 21st, and 27th. During the July 27th test on the NASA spaceflight livestream, the can crusher actually partially crushed B7.1. The audio you're hearing from this test is from Andrew Keating from Cosmic Perspective. And it really gives you a sense of how much force was being applied when the stringers buckled. This was just the top of the tank, which is a glorified testing interface. The bottom was the main area of focus for this test, so the top was really just something to press down on. But this was still pretty rough, so B7.1 returned to the production site to be repaired. In the meantime, SpaceX got to work on the real Booster 7, which had returned to the launch site about a month before and was preparing for its first spin prime tests. The goal here was to quickly move to static fire testing now that the thrust puck and aft section had been structurally verified. Booster 7 now had all 33 Raptor 2 engines, its grid fins, and a variety of other new pieces. Once on the pad, Booster 7 performed an igniter test for the first time with the Raptor 2 engines. And then from there, it was time for some more serious engine testing to occur. July 11th, 2022, the day of the first 33 engine spin prime. When all 33 engines spun up, the mixture of methane and oxygen beneath the OLM decided to detonate. Zach put out an episode after this happened, which was a deep dive explanation into what caused this event, so I recommend checking out that video after this one if you happen to be new to the channel. Booster 7 then rolled back to the Mega Bay for repairs. Ship 24 was the next to return to the launch site, looking nice with its new paint job. It was mounted on suborbital pad B and conducted 7 spin primes in various configurations. On August 9th, Ship 24 conducted a 2-engine static fire using a center engine and a vacuum engine. Booster 7 was also back out at the pad by this point in time, now only sporting the 20 outer Raptor boost engines. 2 spin primes were conducted on August 8th, and the next day, Booster 7 performed the very first single-engine static fire on the orbital launch mount. Another static fire happened 2 days later, but this time it lasted for a duration of 20 seconds to test Booster 7's autogenous pressurization system. Autogenous pressurization, that's a term we hear thrown around a lot, but what exactly is it?
Well, I've explained this on many past episodes, so this time I'll talk about it from a conceptual point of view instead of going in depth on how it's accomplished. Autogenous pressurization is a method of pressurizing a spacecraft's propellant tank using the propellants themselves. In this method, the liquid propellants are vaporized inside of the engine, and a small amount of the resulting gas is used to build up pressure in the tank. The pressure generated by the vaporization of the propellant is used to force the remaining propellant out of the tank and into the engine. It's important to note that as the engines are throttled up, the volume of propellants consumed will increase, and therefore the amount of gas being diverted back to the tanks will have to increase as well. As more engines are firing, the system must be dialed in to balance the pressure inside of the tank to prevent them from exceeding the max pressure rating or collapsing the tank once it falls below its minimum operating pressure. So this test would have to be conducted again in the future using more engines to make sure that it's performing as expected.
Well, after this static fire, Booster 7 returned to the high bay to receive the center 13 engines. When it returned, it conducted a couple more spin primes and attempted a 3-engine static fire. However, it seems that during this test, only 2 engines actually ignited, and 1 auto-aborted during the spin-up. Either way, it looked like a good burn. After this, SpaceX conducted the first 33-engine spin prime since the anomaly that occurred back in July of that year. Taking a step away from Booster 7 momentarily, B7.1's repairs had finally been completed, and it was back out at the pad. During B7.1's stay in the mid-bay, SpaceX had cut off the damaged area around the top and added a new interface piece for the can crusher cap. At the pad, it conducted 2 more structural tests, and you can even see the outer 20 pistons doing their job once again, pulling down on the tank. And it looks like B7.1 successfully passed testing. Following this test, we saw B7.1 and the E-Dome test tank, which we'll talk about in just a little bit, move over to the new Massey's testing site. Massey's is an old gun range that SpaceX now owns and is converted to a cryogenic testing site. Today, cryogenic testing can be conducted on test tanks and entire ships. In the future, we expect that boosters will be able to make the journey over to Massey's as well. Stepping away from Massey's, Ship 24 was undergoing some testing at this point in time and conducted a 6-engine static fire. Some unexpected work followed this, but in the meantime we can talk about Ship 24's counterpart, Booster 7. Now back on the orbital launch mount, it conducted several spin primes over a span of 7 days.
Yo, I hate to interrupt, but do you think we could skip all these spin prime tests?
No.
Damn. Alright then.
Spin prime tests are important for verifying that all of your engines are functioning as expected before firing them. These tests essentially take the engine all the way up to the moment of ignition, except with the igniters disabled. It's essentially an aborted static fire in some ways. By performing these tests, SpaceX gains a lot of data that allows them to know for certain that they won't have any unexpected failures that could cause an explosion on one of these Raptor engines on startup. So, this series of tests were followed by a 7-engine static fire on September 19th. SpaceX was cautiously working their way up to static fires with higher engine counts. After this, Booster 7 once again rolled back to the production site for what SpaceX referred to as robustness upgrades. When it returned, Ship 24 and Booster 7 were fully stacked on the orbital launch mount for the very first time, which was pretty exciting. There's no doubt that this stack looked much cleaner overall compared to Ship 20 and Booster 4. Together, they conducted multiple cryogenic propellant loading tests, likely the single-species propellant loading test that this slide from NASA was referring to. Around this time, over at the Massey's testing site, the E-Dome test tank was getting set up.
Timeout. Why do they call this an E-Dome? Is there something significant about it that warrants the break from the typical test tank nomenclature?
Well, this is actually how it was labeled by SpaceX. We've been assuming that the E probably stands for elliptical or ellipsoidal dome. This test tank uses brand new flatter domes made out of stretch-formed panels, and it was stacked all the way back on June 3rd of 2022.
So what is the reason that they would want to switch to this type of flatter dome design?
Well, to answer that, let's look at the current dome design that SpaceX is using on Starship. These domes are made out of a total of 38 pieces that all get welded together. These are also still believed to be stamped panels like Allan described a few years ago. These newer domes are only made of 19. The long panels that make up the dome are also now stretch formed. Here's an example of how stretch formed panels are manufactured. This is a change that was also implemented on the nose cones of the ships. These changes allow production of the domes to be faster, and it also reduces the number of welds that make up the dome, reducing the chances of introducing weak points. If you shift the domes just right, you should be able to keep the same propellant volume while also slightly increasing your usable payload volume. Alternatively, you should be able to slightly increase the amount of propellant volume in the tanks while keeping a similar usable payload volume. Overall, these domes are easier to make, simpler, and are a much more efficient design altogether. E-Dome rolled out to the launch site after it was stacked, and it really didn't do much during its stay. It appears that SpaceX didn't want to interrupt operations at the launch site for testing that didn't directly relate to Ship 24 and Booster 7. In August, it moved back to the Sanchez site, and then went out to the Massey's testing facility. We didn't even know that testing had begun, but during a flyover, Mauricio for RGV aerial photography saw E-Dome all frosty, so we contacted Lab Padre and had him swing over Sapphire Cam just in time to catch this. The dome cap in the center of the forward dome had been blown off. Not a great result. A later flyover showed that whatever remained in the opening had been cut off. Over the next few weeks, crews repaired the test tank and replaced the dome cap. Sometime between October 20th and 29th, E-Dome was tested again, this time ending with what would have been a very large pop. In this aerial photo, we can see that the entire lower dome shot off of the tank, which goes to show that this must have been under a considerable amount of pressure. We haven't heard anything official about this test, but we know that these domes are already being implemented as booster common domes with booster 10 and onwards, so it probably went well enough. SpaceX's next Starship made it out to the launch site at this point, and Ship 25 was ready to conduct some cryo testing on Pad A with the thrust rams. So, on November 1st, it conducted its first cryogenic pressure test, followed by a second on November 2nd, and a third on November 7th. Ship 25 then returned to the production site for engine installation, but this process didn't go exactly how we expected. We'll discuss that in a little bit. Back to B7, with whatever the robustness upgrades were, having been completed, it returned to the pad and conducted a spin prime. This was the first time SpaceX used the new FireX and detonation suppression system that would now be active during all engine tests from here on. Zach has a video on that as well if you'd like to learn more about it. This spin prime was followed by a static fire of 14 Raptor engines on November 14th. About 2 weeks later, on the 29th of November, it conducted an 11-engine static fire with a full liquid oxygen tank, once again testing out the Autogenous pressurization system. This static fire lasted for about 13 seconds.
An interesting thing about this test is you could actually see the gaseous oxygen being purged from the LOX tank. I think this may be a sign that the Autogen system was actually overperforming during this test, causing the booster to automatically release the excess pressure.
Yeah, great observation. Following this test, as seems to be typical for Booster 7, it went back to the production site for finishing work, ahead of its launch attempt. We're now going to talk about Ship 24 for a bit. In the latter half of 2022, SpaceX appeared to run into multiple issues with the vehicle, most notably the payload bay and the aft section. Both of these, if left unchecked, may have resulted in a mission failure. Let's check it out. After Ship 24's 6-engine static fire on September 8th, 2022, SpaceX got to work setting up scaffolding directly beneath the sliding payload bay door. Ship 24 was, equipped with a Starlink version 2 deployment system. An internal racking system allowed 2 stacks of Starlinks to be loaded side by side. There's a built-in lifting mechanism that grabs onto the newly loaded satellites and then lifts the entire rack so another pair can be loaded underneath, like a pallet loader. The Starlinks are loaded onto the ship using this white box, which is lifted using the high bay bridge crane and gets mated with the ship so that the Starlink V2 sats can be transferred from the loader to the ship with relative ease. This is a convenient way for SpaceX to avoid constructing a large payload integration facility this early in the development process, even though they have stated that there will be a facility constructed for this purpose in the future. Once in orbit, the Starship will deploy its payload by shooting them out of the small door like a Pez candy dispenser. But Ship 24 didn't get to keep this system for long. With this new scaffolding set up beneath the door, SpaceX got to work. What exactly did they do here, Zach?
By now, a lot of you are probably already aware that the payload bay on Ship 24 and Ship 25 have both had covers installed over the doorways. We haven't received any official explanation for why this was done, so we have to examine the available evidence as closely as possible to try to come to these conclusions ourselves. So let's take a step back and start by examining the basics of the overall design of this version of the Starship payload section.
The first step in creating this payload bay is to form a 5-ring barrel and install all of the internal stringers. On Ship 24, there are 88 stringers, and on Ship 25, they increase this to 94. You can see these stringers from the outside of the ship thanks to the weld markings on the skin of the vehicle.
You will notice that below the weld line for the forward dome of the ship, there are no stringers. The reason for this is because both the liquid methane and liquid oxygen tanks of the ship get most of their strength as a result of being pressurized up to somewhere between 6 and 8 bar. This is equivalent to a range of roughly 87 to 116 psi. Pressurizing the propellant tanks to this level will have a stiffening effect on the tank walls and the entire rocket structure. This is because the pressure inside of the tank exerts a force outwards against the walls, which helps resist deformation. Essentially, by counteracting external stresses on the tank, it becomes more resistant to buckling.
The payload section, on the other hand, will be unpressurized while the door is open, and when it's closed, should only hold about 1 or 2 bar of pressure during flight operations. This is why the stringers are necessary in this area in order to make up for the reduction in wall strength due to it being a non-pressurized space. I believe that these stringers primarily increase the strength in the axial direction. These forces will be greatest during max Q, but they will also come into play during re-entry. After the stringers are installed, additional hoop stiffeners are added as well. These hoop stiffeners have teeth that allow them to slot between each of the stringers and contact the inner wall of the ring section. They are welded both to the stringers and the inner wall, which makes it so you can easily see them from the outside. Anytime we see these dotted weld marks in between the vertical lines of the stringers, we know there are hoop stiffeners present. These hoop stiffeners complement the stringers by increasing the strength of the vehicle in the radial direction. I think these forces come into play primarily during the re-entry phase, but I'm definitely not an expert in aerospace structures, so take everything I'm saying on that subject with a pinch of salt. Anyways, with the internal reinforcements installed, the next step is to cut an opening into the barrel section of the ship in order to create the actual doorway. I think that the height of this door makes it appear like it wouldn't be that big of a deal when it comes to how it affects the overall structural integrity. But when you take a moment to consider the length of the opening, it's really quite staggering. This opening is just over 7.2 meters wide, which is a lot considering the ring sections of the Starship have a diameter of 9 meters. If you look at the cross-sectional view from above, you can see that the angle made by the opening is about 108 degrees, which represents nearly 30% of the total circumference. Because the doorway is located at the bottom of the payload section, it means that it must support everything above it. This includes more than 80% of the nose cone structure, both forward flaps, and all of the COPVs that are mounted in the top of the nose cone. This also includes the header tanks, which will add several tons of additional mass to the top of the structure once they are filled with liquid propellants. Oh, and there's also a few thousand TPS tiles as well. Not only must it support all of that weight, but it will also be required to withstand the dynamic drag forces that will be exerted on it during the max Q phase of flight. Without the gigantic hole in the barrel section, the static and dynamic forces would be relatively uniform through the entire 5-ring stack, increasing proportionally as you move down towards the forward dome of the methane tank. These forces increase during flight as the vehicle approaches the point of maximum aerodynamic pressure. Let's take a look at how that changes once you introduce the doorway. Keep in mind that this is just a conceptual representation and isn't based on actual simulation data, but you can see that with this large section of material removed, the path of those forces will now have to be redirected around the opening. This will create an area of significant increased stress concentration around the left and right edges of the doorway. Something has to be done to compensate for the additional stress that will be experienced in these areas. If this was an observation window that we were talking about here, this problem would be solved by placing structural supports over or inside of the opening, similar to what we see in conceptual renders of the Starship. These supports could be made as large as necessary to accomplish the job. Not only this, but the windows themselves would ideally be integrated into the outer walls of the ship so that they become load-bearing structures that contribute to the strength of the hull. Unfortunately, the sliding door for the current version of the Starship Payload variant is not integrated into the walls, but is instead mounted on two railways above the doorway. I wish I could show you what these look like, but we have no idea because SpaceX is super sneaky when they install these doors. But what we do know is that this door is a completely separate structure that is essentially being suspended from the inner walls of the ring section.
So what did SpaceX engineers do in order to make up for the fact that 30% of the structural supports for the Starship payload section had essentially been eliminated?
Well, after Ship 24 was fully stacked in the high bay, they installed 3 sets of long stringers on either side of the door, which extend from about 2.5 meters above the opening to 5 meters below it. Initially, they believed that this would be enough to reinforce this major weak spot that was created by designing the door in this way. But shortly after Ship 24's 6-engine static fire attempt, they decided that this was simply not going to work. On the morning of September 15th, SpaceX workers slipped a thin sheet of steel underneath the vertical stringers on the edge of the doorway. Over the following 8 days, they added an equally thin frame around the top and bottom of the doorway as well. This strip of steel creates a 4-inch or 10-centimeter overlap around the opening, which should help increase the stiffness of the frame.
Now, it might not look like much, but it's important to remember that the Starship is constructed out of 4mm stainless steel. So this little strip is doubling that, so it's now 8mm.
After this frame was welded around its entire perimeter, it was finally time to install the cover to completely seal the opening. Before they did this, several holes were drilled through the sliding door to allow the void space between the door and the cover to equalize to the same pressure as the rest of the nose cone. After the cover was lifted into place and properly positioned, they temporarily secured it using small tack welds spaced out along the perimeter. When we zoom in, you can see that there are small rectangular holes along the entire length of the stainless steel cover. Each of these received 2 spot welds on the top and bottom edges of the cutout. Once it was supported enough by the tack welds, they were able to remove the lifting jig and then complete the final weld around the entire perimeter of the giant metal cover and also around the perimeter of all 220 cutouts. So yeah, this was a lot of hand welding that had to be performed over the span of about a week. A few weeks later, we also noticed some new weld marks appear above the door cover, which is a sign that some additional reinforcements were added to the interior of the ship. These were most likely some sort of bracket to hold the sliding door in place to prevent it from moving. On Ship 25, they took a similar approach when sealing the door. SpaceX may have welded the door to the edges of the cutout for the opening, but it's hard to be certain. This would effectively make it so that the door is now actually contributing to the structural integrity of the payload section by bridging the gap and creating a new path for axial forces to pass through. But, like I said, we have no proof of this. Anyways, after Ship 25's door was welded, they removed the small stringer supports that were initially on either side of the door and installed a similar but larger weld doubler frame to go around the perimeter of the opening. These are also referred to as super stringers by SpaceX, and that's likely because they essentially serve the same purpose. You can see there is additional material used in the high stress zone that we mentioned earlier.
So when it's all said and done, there are now 4 layers of steel sheets that overlap around the frame of the opening, which means there are nearly 16 millimeters of structural framing now in those areas instead of 4. There's 8 millimeters of material in the center, not including the void space between the 2 sheets or the structural supports that are on the back side of the door.
So, Ship 24 and 25 now had their doors sealed shut. But the question remained for many, why do this? We definitely don't know for certain, but there seems to be a few possibilities. This is what we can say with a fair amount of confidence. There now seemed to be a design flaw. Both Ship 24 and 25 had their doors sealed. With Ship 25, this seemed totally unprompted, and it had only completed basic cryogenic tests, nothing that would have caused damage to the system, unless something occurred during transportation. So what could have gone wrong? SpaceX had not conducted any structural verification testing on the PEZ system at this point in time. So it seems that they either conducted computer simulations, or something happened to the real vehicles themselves. SpaceX sealed Ship 24's door right after the 6-engine static fire, which we know was violent. It's possible that the vibrations from the static fire could have caused some damage to the dispenser system as a result of an inherent design issue with it, but there's no way to really prove that. If computer simulations found that the Pez dispenser was unstable, it would be hard for us to know that as well. But sometimes, to find what the issue was, we can look at the solution and work backwards. So let's look at what SpaceX did with the Pez dispenser after Ship 24 and 25. This oddly takes us to one of the first Payload Bay Pathfinders, which was constructed before Ship 24. It was originally designed with a door that would have operated like this depiction from Ryan Hansen's Space. This design used a large door that took up the entire 5-ring payload barrel, but there were some issues with it. After it sat outside for quite some time, it became clear that this design wasn't exactly stable. And you can see that the top portion above the door had started sagging and was being held up with chains. Anyways, on the opposite side of its large door, SpaceX cut out a Pez dispenser hole for some more pathfinding. On the right-hand side of this barrel, we can zoom in really closely to see a lot of doubler plates stacked on top of each other. So they were pathfinding reinforcements, and we knew that a fix for the Pez dispenser system was on the horizon. Now it seems weird that they would give it 2 smaller door cutouts, but it eventually became clear that this barrel was so structurally compromised with all of the holes in it now, that crews had to cut around the internal reinforcements. Many people have been wondering if it would be worth doing 2 smaller doors for deploying Starlink satellites though. The way I see it is that if you have to do a big door eventually, even ignoring any fitment issues that may arise from rotating the satellites 90 degrees, it might just be worthwhile to figure out how to do a wide cutout sooner rather than later. It's just delaying the inevitable. But regardless of that, with all of these extra doubler plates, we are waiting on these changes to be implemented. Ship 27 and onwards implemented these changes, and looking at Ship 28's door, we can see that these doubler plates had been added on each side of the door, adding up to a total thickness of about 16 millimeters of steel in those areas, assuming these are all 4mm plates. Additional doublers continued around the perimeter of the door, but it's only one layer. Another addition was 9 remove before flight locking plates that hold the door in place. Now this could be as simple as a safety feature, to make sure the door stays closed on the ground. Maybe it's to keep the door secured during ground testing itself. Either way, we know that SpaceX had suddenly decided to heavily reinforce the opening in the side of the ship, which may suggest that Ship 24 and 25 had a structurally compromised opening, but it's not for certain. If this was the case, during the ascent or re-entry portions of flight, the doorway could have tried to deform and even begin to fold. If this happened, the vehicle would likely be destroyed pretty quickly. The aerodynamic forces would likely try to tear the vehicle apart, and they'd probably succeed, but we'd also see the methane and oxygen pipes that run up the payload bay get damaged. If this happened, and they possibly ruptured, the pipework would lose pressure, and you may have an explosion occur. Overall, you don't want a compromised payload bay. As a side note, one of the things that many people have pointed out are these 2 struts on the payload bays during production. They've been used since Ship 25, and may suggest that the door requires extra support during the production process to prevent it from sagging. Once stacking of the vehicle is completed though, these are removed and the areas where they're mounted get cut off. So, these new modifications are yet to be tested out in real life, but these are definitely things that we believe should eventually go through some actual structural verification testing. We'll need to keep an eye out for a potential test article featuring the payload bay that would undergo testing. This more than likely won't happen before the first orbital flight though.
Well, I guess it doesn't really need to, especially since Ship 24, 25, and 26 can't deploy satellites, so these changes won't really come into play for a while.
Yeah, exactly. Now, this is only when some of Ship 24's issues began. Another section of the ship that SpaceX did not structurally qualify before integrating it with the vehicle was the aft section. Now, I'm not talking about thrust ramming the dome. I'm talking about the unpressurized skirt area, which is a key area of concern because it's a major component of what would be considered the Starship's interstage. I'm not sure if I need to explain why it's important to avoid a collapse of the interstage 1 minute into flight during max Q. So, SpaceX constructed a test article to test out both the skirt structure and the aft flap hinges. A 4-ring aft dome sleeve that matched Ship 24's construction was developed and sent over to the can crusher at the end of September in 2022.
And with this test came yet another new configuration for the can crusher. Really gotta love how versatile this testing structure is. In order to test a Starship aft section on the can crusher, SpaceX needed an adapter in order to interface with the 20 hold-down positions, which are normally tailored for booster testing. This black ring was delivered several months in advance for this job. It would later have adapters for the 20 clamp positions installed so it could sit on top of the can crusher mounts. The cap was modified as well. They added an appendage that would allow it to interface with the mounting positions for the aft flaps of the Starship, similar to what we saw in the nose cone jail in Part 1.
This allows realistic flight loads to be placed on the aft flap mounting points while the cap is being pulled down by the hydraulic pistons.
So, with it on the can crusher, we believe that testing was conducted on October 7th, when Remedios Avenue was closed for testing and an aerial work platform was presumably set up with a camera to watch the article. After the test, many people noticed that some of the ring welds had dented inwards. This was a structural failure, and it was unclear at the time what their next steps would be. What most people didn't notice is this photo from Mauricio for RGV Aerial Photography when the article returned to the dome yard. Not only had the aforementioned ring weld dented inwards, but so had the area around the quick disconnect panel. The quick disconnect, or QD, is used to supply the vehicle with power, liquids, gases, and other consumables. There's a lot of very delicate pipework behind this, so this is actually really bad.
Yeah, I mean, that's one way to put it.
SpaceX had to get to work right away to find a solution, because this directly impacts Ship 24 and therefore the first orbital flight test. So this test article went into Tent 2, and we got a look into the tent a couple weeks later to see the stringers that were being added all around the QD after using hammers to bang out the dents. The actual QD panel appeared to have been removed and replaced as well. When it went back to the can crusher, it looked like this. Now, if you've been watching this program fairly closely, you'll know that no ships look like this. So my best guess would be that SpaceX did a quick fix to allow flap hinge testing to continue. And it seems that testing went well. This article was removed from the crusher and still remains in the ring yard as of March 2023. But there was still an issue to address. The QD and ring weld issue hadn't actually been resolved, and if the quick disconnect was to rupture during flight and the pipework was to get damaged, well, I don't think I need to tell you what a mixture of oxygen and methane likes to do in an enclosed area, because the QD pipework is above a steel false sealing layer inside of the skirt, where many of the electrical systems are found. You'll also likely lose pressure in much of the pipework, and some of this is directly connected to the engine feed pipes. Over at the suborbital launch site, a tower of scaffolding was being erected around Ship 24, and tiles were being removed around the lower 3 rings of the aft section. By doing this, workers were able to access the area directly above and below the ring welds. Once the tiles were removed, they welded a doubler plate over the ring welds, which is really the only real alternative to placing stringers over the area, which is not an option on the protected side of the ship without some major extra work. So this was at least part of the solution. For these top 2 rows of removed tiles, we never actually found out what they did, but presumably some kind of reinforcements were added on the ring welds. We then saw the tiles get replaced and the scaffolding would eventually come down. After this, the work on Ship 24 did go silent for a little while, because it was time to qualify these changes before anything more happened. So of course, yet another test tank was produced. Ship 26.1 is a test tank made out of a Starship aft section and a forward dome, just to be used as a testing interface like B7.1. Our first sign of impending design changes was this photo from Starship Gazer looking into the Mega Bay. Crews were measuring out areas around the QD panel, and a later photo would show that doubler plates were added around all 4 corners of the QD, increasing the thickness of the area likely to around 8mm. 26.1 also had doubler plates like we saw added underneath Ship 24's heat shield, added all the way around on the lower 3 ring welds. I don't think many people realized this at the time, but S26.1 was critical in order to confirm that Ship 24 would be able to stay stable during its flight. We've previously discussed how strain gauges are used to measure deformations in the steel, and the placement of these definitely tells us what SpaceX was looking at. We can see 2 strain gauges by the quick disconnect, some more up by the weld line for the aft dome, some on the stringers that reinforce the aft dome weld, and some more by the doubler plates that were put over the ring welds. S26.1 was moved to the Massey's testing site and conducted at least 1 test on December 21st, 2022. It might have been tested more, but due to the lack of coverage out at Massey's at the time, we can't be sure when that would have been. The good news is that Ship 26.1 seems to have passed testing, and SpaceX was able to proceed with adding these modifications to Ship 24.
Well, if this test article had failed, they could have just skipped over Ship 24 and then went to Ship 25 next, right?
Well, it's not that simple. And this is one of the few things that we hadn't quite anticipated when we started looking at 26.1 a few months back. Here is a photo of Ship 24's aft section, and we're going to look at the welds just a little bit. We can see the dashed vertical welds, which indicate there are 96 vertical internal stringers on this section. Alongside these stringers, we can count 8 hoop stiffeners from these welds. Together, these form the primary reinforcements in the aft section. There are others around the aft flaps like this large weld doubler, and this is because the hardware to support the aft flaps makes it so hoop stiffeners can't pass by on the interior. Anyways, 96 internal stringers and 8 hoop stiffeners. Remember that. Looking at Ship 25's aft section right after it was flipped, we can see the same 96 vertical internal stringers in addition to 6 hoop stiffeners. At this point in time, the 2 located in the middle of the barrel were yet to be added. But looking at Ship 25 later on, which is more difficult, we can see that they are still present. They're just added later on in the production process. On to Ship 26 then. We can see the same stiffeners like previous, and it's missing a couple that would be added later after this photo was taken. Ship 27 is next. It's the same too. Over to Ship 28, in this photo it's upside down, and is missing a couple of them like Ship 25 when we talked about it, but these would eventually be added, making this the same too. I think you can see where I'm going with this. All of the aft sections had the same general reinforcements, simply because without any structural testing, how would SpaceX know to change anything? So now, every single aft section that had already been produced needed to receive the same modifications that S26.1 had, which at the time was at least up to Ship 30-ish. To review, that meant 4 doubler plates would be added on the 4 corners of the quick disconnect panel, a frame piece would be added to the top edge of the quick disconnect panel, and the lower 3 welds on the vehicle would all have doubler plates put over top. Ship 24 is now visible with the doublers around the QD panel and the ring welds, like 26.1. Ship 25 is visible with doublers around the QD panel, and, well, they started on the ring welds. Ship 26 has them on the QD and the ring welds, just like the previous 2 ships. Ship 27 has them in those spots too. If we brighten up this photo inside the Star Factory a bit more, you can even see them on Ship 30. Let's be clear that this wasn't an issue with Ship 24. This wasn't an issue with Ship 24's generation. This was an issue with Starship as a whole, and absolutely everything was impacted.
Okay, hold on a second. You said that they've already finished all of these reinforcements on all of the ships, but you also said that they only started on Ship 25.
Well, that's true. I don't think most people have mentioned it, but when Ship 25 returned to the high bay to receive its 6 Raptor 2 engines, SpaceX did start adding the reinforcements on the aft section while they were sealing the payload bay door shut. But they don't actually seem to have finished. Looking at Ship 25, you can see they only ever put this small doubler on the middle, in addition to doublers around the QD plate. Up at the Pez dispenser door, the cover was never actually completely welded on either. It looks like crews started doing the final weld pass, but we can still see parts that visibly weren't welded. This was weird at the time, and it still is. Maybe it's suggesting that SpaceX hasn't intended on flying Ship 25 for a while. Or maybe it's looking too deep into this. Either way, it's quite strange. Overall, SpaceX dodged quite a few bullets with all of their ships, because thankfully these design flaws didn't force them to abandon every ship that was currently under production. That's one of the benefits of stainless steel. What is a bit concerning here is that such a seemingly large disconnect between processes was allowed to happen. And as Zach mentioned at the beginning of this investigation, this was a direct result of Ship 20 and Booster 4 being scrapped. If we look back to March of 2022, the retirement of these 2 vehicles meant that SpaceX now wanted to rush out the new ship and booster, which happened to both feature some pretty major upgrades. In doing so, the vehicle manufacturing seems to have taken priority over vehicle testing and design qualification testing, which I think was part of the long-term cause for these issues with Ship 24. Instead of verifying these new designs to make sure that they were A-OK, the designs were implemented into the vehicles right away. To me, it seems that SpaceX had at least some degree of confidence that these designs would be fine, and their simulations and math may have backed that up. And by no means do I think I know better than them, but I just feel like this sudden rush with Ship 24 and Booster 7 put a lot of very crucial things on the back burner. We're in March of 2023, and SpaceX still hasn't even finished testing with verifying absolutely critical components of Ship 24. The reality is that with rapid iteration, sometimes things like this might happen. Nobody's really done anything like this before. The solution to this is that SpaceX will likely put a bit more priority on the structural qualification, which ultimately may save time and negate the need to go back and retroactively modify 7 aft sections at the production site. But with this aside, they have to finish up verification testing. So it's time to look at the last couple test articles on the agenda. One of the test articles that SpaceX tested at the end of 2022 was Booster 6. Booster 6 was skipped in favor of Booster 7 at the end of 2021 and was stacked to become a test tank in December of that year. It's made out of a booster forward dome and a booster common dome. However, the common dome was capped off to create an enclosed tank. B6's counterpart, which we've heard referred to as 6.1, was a ship leg skirt originally believed to be assigned to Ship 22. Ship 22 is believed to have stolen Ship 23's leg skirt during the production process, so this one was left roaming around. These parts sat around for about a year until the end of 2022. The skirt received reinforcements to make sure it didn't collapse during the test, and because it was an old and irrelevant design, collecting data about it really didn't matter. But the integration of B6.1 would be structurally qualifying the connection between the ship and the booster, in addition to the booster half of the Interstage, which still hadn't been changed all too much from B6's design. It was assembled on the can crusher and the cap was placed on top. November 14th and 15th are believed to be when this was tested, and as far as we can tell, it passed perfectly fine. There have been a few more trials with various test articles since this, but for the sake of this video and the uncertainty of what's still happening with these, we're just going to talk about one of the other tests that SpaceX is in a rush to complete before this launch. Ship 24 implemented a new design of nose cones, now using fewer, stretch-formed panels instead of many stamped panels like was on Ship 22 and prior. The old design was tested in the nose cone testing cage back in 2021 using nose cone 12. So SpaceX waited some time to actually test this, but they chose to test it, and truthfully for a while we were a bit worried that they wouldn't. Nose cone 31 first deviated from the standard production process in November of 2022, when SpaceX suddenly stopped putting heat shield tile pins on it. In the coming months, the flap hardware was developed and we eventually saw the tip get removed, just like NC-12 a couple years back. It would roll over to the Sanchez site on February 14th and was then placed on the nose cone cage base. I'll let Zach discuss how this testing structure was configured for nose cone 31.
Well, it's important to note the obvious fact that this nose cone is missing the payload section. So, since SpaceX is only trying to verify the structure of the tapered nose section, they had to shorten the testing structure to about half of its original height. The nose cone has a single 9-meter ring added below the nose cone section. This ring has an access hatch that allows SpaceX workers to have a way to enter inside of the structure to service the hydraulic pistons inside. This ring section is welded down to the base structure with extra reinforcements on the outside, and stringers on the inside to ensure that if this test article buckles under pressure, it won't fail due to this ring, which isn't actually part of the test. Inside of the structure, there are 3 small pistons on top of a platform that will be used to pull down on the cap from the inside. Up top, they again have 2 pistons to pull the nose cone in different directions to simulate re-entry forces. So, other than the changes that were made to the test structure itself and the lack of a 5-ring stack, this is relatively the same as what was done with the SN12 nose cone. We likely won't see this test when it's performed, even though there are cameras pointed at it from a distance. It'll be very hard to determine when it happens, but it's safe to say that it will occur before the first orbital flight test.
And that's good news, because once that's completed, we can confidently say that SpaceX has now structurally verified every section of the booster and Starship. Minus the 5-ring payload section, but hopefully that won't matter for this first orbital test flight. Speaking of which, on January 23rd of this year, SpaceX completed their first ever full stack wet dress rehearsal, successfully filling the Starship first and second stage with liquid propellants and taking them through a complete launch countdown sequence. This includes everything that will happen during a real countdown to T-0, other than retracting both quick disconnects and igniting the Super Heavy booster's 33 Raptor engines. It was incredible how smooth this went, and I'm sure that completing this on their first attempt really got the team fired up. And if that somehow wasn't enough excitement, on the 9th day of the second month, SpaceX finally performed a not quite 33-engine static fire test on the orbital launch mount. This was a relatively low throttle test, peaking at about 47% of available thrust. I say available thrust because SpaceX manually aborted one engine and another auto-aborted for unknown reasons. Overall, everything went incredibly well, and if we're lucky, we should see the first launch occur sometime in April, and I want to personally wish SpaceX luck. So, where does that leave us? Well, if you get one thing out of this episode, We hope you were able to gain a better understanding of how structural qualification testing plays a major role in the Starship development process. It is very critical for this to be performed properly, and every time SpaceX makes a major change to the design of the booster or Starship, we should expect to see them begin the qualification process all over again. And I can guarantee you that there will be a lot more of it to come. This is a pretty monumental task that SpaceX is taking on here. Keep in mind that there are at least 5 planned variants of the Starship, which will do everything from placing payloads into orbit, orbital refueling, return humans to the moon, and hopefully send them to Mars as well, which will require both crew and cargo variants. This is something of far greater ambition than what we saw accomplished with the Saturn V. And that's kind of crazy because at its peak, the Apollo program employed more than 400,000 people and required the support of over 20,000 industrial firms and universities. The last time we heard, SpaceX has less than 2,000 employees working on the Starship program. So if this kind of stuff interests you, then you should probably come work for SpaceX because they really need your help. Like yesterday. Anyways, I look forward to keeping you updated on where the situation goes from here, and hopefully Jax and the Ring Watchers will continue to track these hard to notice changes because we really wouldn't be able to cover this topic anywhere near as thoroughly without them. So thank you, Jax.
Yeah, happy to help anytime.
And in the meantime, be sure to follow the Ring Watchers on Twitter for more updates. If you enjoyed this episode, then do us a favor and hit that like button and subscribe to the channel if you haven't already. I've decided to go full-time with the CSI Starbase YouTube channel, which means you will likely see a significant increase in content that we will be putting out in the coming months. If you would like to help support the channel while I make this transition, then you can do so by becoming a monthly supporter on Patreon or by joining as a member of the YouTube channel. Before I go, I also want to thank Chameleon Circuit for their hard work putting together the detailed renders and animations used in part 1 and 2 of this deep dive investigation. And I also want to thank Geoff for constantly improving the quality of the production that goes into these episodes every time we release a new one. Hopefully all of you returning viewers can appreciate the way that he's able to level up each time as well. And speaking of hard work, huge shout out goes to Lab Padre, NASA Spaceflight, RGV Aerial Photography, Starship Gazer, Cosmic Perspective, and all of the other Starbase photographers and 3D artists whose content was used in this episode. Thank you for doing what you do to document history in the making. You can find the links to all of their various channels in the description. Last but not least, thank you to Squarespace for sponsoring today's deep dive investigation. All right, everyone, I'll see you all next time. For now, the Stage Zero Zach, signing off.